Well, hello again, all of you geometers and people that are trying to learn about some geometry. Welcome back to my page. Today we're going to talk about some transformations that we do in geometry and grid stuff. So we're going to do it on a grid. So to start with, in general, three of these four transformations that we normally talk about in geometry are called isometries. Okay, and isometry is a vocabulary word that means that this is a translation or a transformation that preserves distance. Okay, it's a transformation that preserves, that makes it so that distance doesn't change. That is awful. Handwriting, sorry. That preserves distance. Okay, in other words, the shape that you end up with is the exact same size as the shape you started with. Okay, nothing changes. Oftentimes this is referred to as a congruence transformation. And isometry is a congruence transformation because the thing that you end with is exactly the same as the thing that you started with. They are congruent. Their segment lengths are the same. Their angle measures are the same. Everything about the things that you are dealing with is the same. Okay, in fact, so some other ones, the thing that you end up with, the shape after your transformation, is called the image. Like when you look into the mirror, you see your own image. You're seeing the reflection of yourself. So that's the image is what you get when you end your transformation. What the beginning transformation is called your pre-image. Okay, so the thing that you start with, your original picture, is your pre-image. You do some transformation to it. You end up with an image of that. So the three isometric or isometry transformations are translations, which is a slide, simply a repositioning of a picture on a grid. So you take it here and you slide it over there. Everything stays the same. The orientation is the same. The angles are the same. Everything looks exactly like it's supposed to. So you're simply moving it around. A reflection is where you are flipping it somehow. So if your triangle looked like this maybe, and we had a vertical line of reflection, okay, its orientation would change and it would end up over here. This isn't an exact drawing, but the rotation or the reflection would end up and the orientation would be a little bit different. Okay, it would be opposite of what it started with. And a rotation is a spin. Okay, if we had this as our triangle and we had some type of a center of rotation and we were spinning this somehow, maybe 180 degrees, it would end up over here like this. Okay, so we're spinning every point. This point spins around to here, the top point spins around to there, and so on and so forth. Okay, so the isometries are translations, reflections, and rotations. Okay, we'll get into some problems here with this in a minute. And then we'll talk about our last transformation, the dilation, which is not an isometry. So, a translation, once again, a repositioning on the graph. So there are two ways that we can translate things. One way is by a rule, a geometric rule, or an algebraic rule, rather. So this says every point on the graph, change it in this fashion. Okay, add or subtract some value to x, add or subtract some value to y. Okay, so this is changing it in a left-right fashion. If we are subtracting, that means you are moving things to the left. If we have an addition problem, you're moving points to the right. Okay, just the x value. Okay, x plus or minus a. The y value moves things up or down. So if we have a minus, that's going to move every point down a certain number of units. And if we have a plus, that's going to move everything up a certain number of units. Okay, generally in a high school geometry class, that's what you do. You could also translate by a vector. In pre-calculus, they use vectors a lot more, or in physics. This is just how they write a vector. It has some x component to it, either right or left in the x direction, and some y component to it, up or down, depending on whether it's positive or negative. Okay, it's always in the chevrons these pointy parenthesis looking things called chevrons. That's how you can tell that the translation is given by a vector. Okay, so if this is our point, we're going to move it some distance in the A, say this is positive, and some distance vertically B units, something like that. Okay, so A is of course your x distance traveled, B is your y distance traveled, and this is your vector, your resultant vector, like this. Okay, but we're going to use a rule. So our next problem is a translation that involves a rule. So here I have a triangle ABC on a nice grid, and I want to take every point and I'm going to change it to x plus 5. So I'm going to add 5 to every x point, or move everything 5 units to the right. And I'm going to move minus 6 from every y point. In other words, move every point, the y value, down. Okay, and I can do this quite simply by counting on my grid, which is why this is very nice. So starting at A, I'm going to count 5 units right, 1, 2, 3, 4, 5. And I'm going to count 6 units down, 1, 2, 3, 4, 5, 6. And this is where my point ends up, my new point, or A prime. The translation of A under this rule. 5 units right, 6 units down. Same thing with B. 1, 2, 3, 4, 5 units right. 1, 2, 3, 4, 5, 6 units down. B prime. Okay, that's how we write a translation's point. We're taking B and we're moving it to something else, so the prime indicates it's been changed somehow. C, 5 units right. 1, 2, 3, 4, 5. 6 units down. 2, 3, 4, 5, 6. And here's where we're going to end up with C prime. Okay, so now we are going to connect these dots with the nice lines so we can finish out our triangle. And oftentimes, at least me, I have my students color in the image. So I'm going to color all of these images. Here, this image, I'm coloring whatever color you think this is. Some kids say it's yellow, some kids say it's orange, some kids say it's tangerine, but whatever. So here, the colored thing is your image. The non-colored thing is your original, your pre-image, if you will. So I guess the more I color it, the more yellow it gets. Okay, so that's a translation under a rule. Okay, the x thing moves it left or right, the y thing moves it up or down. So let's talk about some reflections. There are 3 different, usually, lines of reflection. There are vertical reflections, which have horizontal lines of reflection. So here this is going to be, we're going to reflect this triangle across the x-axis. So here is our x-axis. So we draw in this. This is your line of reflection, the thing that's going to divide your graph into portions. And what we want to do is move every point to the exact opposite. So here we have a vertical reflection. The y values don't change, so we just need to count how far away we are. So here we are 3 units below the line of reflection. We're going to end up 3 units above the line of reflection. B is 1, 2, 3, 4, 5, 6, 7, 8 units above the line of reflection. It's going to end up 1, 2, 3, 4, 5, 6, 7, 8 units below the line of reflection. C is 1, 2 units above. It's going to end up 2 units below the line of reflection. Okay, you're always counting perpendicularly to your line of reflection. So a horizontal line of reflection, you count vertically. The x values don't change, but the y values do, because you are moving it vertically. Makes sense. So here's your A prime, B prime, C prime. Let's color in our image. Here we go. So let's verify just for fun. Here we started with an A value of -4, -3. A prime ended up at -4, +3. Okay, and this is always true if you're going to have an axis type reflection. The y's will just change. But we don't always have an x or a y-axis reflection, so don't just get this in your head that it always is just the opposite. Okay, actually very rarely does that actually happen. B is at the points -1, 8. B prime ended up at -1, -8. And you can verify the same thing here for C and C prime. 5, 2 and 5, -2 are the 2 points. So here we have y equals 2. This is another horizontal line through the point +2. So once again, we're going to have a vertical reflection. So every point on top is going to end up on the bottom. Every point on the bottom is going to end up on the top. So here we're still counting vertically, but we count to your line of reflection. So A is 5 units away from your line of reflection. It's going to end up 5 units on the other side, A prime. Okay, so you count perpendicularly to your line of reflection, and then you go an equal distance on the other side. Once again, it's a congruence transformation or an isometry, so these things should be the same. And of course, here we have point C, which is on the line of reflection. It's going to end up staying on the line of reflection. It's not actually going to change. Okay, points on your line of reflection don't ever move. So here we have our new triangle, A prime, B prime, C prime. So we're going to color in the image just to differentiate from what we actually started with. Your teacher might appreciate that if you do it. It might give you a smiley face on your paper. Okay, so we're counting perpendicularly to the line of reflection. So here we have x equals 1 as our line of reflection. That's a vertical line through +1 in the x-axis. So because we have a vertical line of reflection, we're going to count horizontally. We count that A is 5 units to the left of the line. It's going to end up 5 units to the right of the line, A prime. C is 1, 2, 3, 4 units to the right. It's going to end up 1, 2, 3, 4 units from your line of reflection to the left. And B looks like it's 2 units away, so B prime is going to end up 2 units away on the other side of your line of reflection. Okay? So not everything happens across your origin, or across the x or y axis, sorry, not your origin, but the x or y axis. So just be aware that your line of reflection is different than your axes. Okay, so always sketch in your line of reflection and then count perpendicularly, vertically or horizontal, if so it is the case, so you can see how far you need to go on the other side of that line. So here is the image, A prime, B prime, C prime of triangle ABC. So this next example, notice we have y equals x. And y equals x is not a vertical or a horizontal line. It is your 45-degree line that goes through your origin diagonally. So y equals x is a diagonal line. So when we count to see how far away each of our points are, we need to count diagonally now. So we're going to count along the diagonals. Here we have 1 diagonal, 2 diagonals, 2.5 diagonals. A is away because we want to count perpendicularly. So we're going to end up at 1/2, 1, 2. So here we have 2.5 diagonals away in a perpendicular distance. Okay, perpendicular is the quickest way. B, let's see, B is 1, 2, 3, 4.5 diagonals away. So we continue 1/2, 1, 2, 3, 4 diagonals away, and 1/2. C is 1.5 diagonals, so C prime is going to be 1.5 diagonals. Okay, a diagonal is just another unit at which you count. So it's not a straight line unit like it is for horizontal or vertical. It's actually √2 units long, but it's still a diagonal. so we can count diagonally. As long as you stay consistent and do it both ways, you should be fine. So here we have the image, A prime, B prime, C prime, over the reflection across the line y equals x. Okay, this is the one that students sometimes get confused about. But if you count horizontally, notice, you just have to remember, and there's lots of ways to do it. If you count horizontally, this is 3 units away from the line. Horizontally becomes vertical, and then you have to go down that many units. Okay, it works with A also. Here, A is 5 units away horizontally, so it's minus 5 away this way. So, I mean, you can count as long as you remember that you have to reflect it. So right goes down, up goes left, and such and such. Okay, so those are some reflections. You have horizontal, vertical, or diagonal reflections. Just be aware of which one you're given in your problem, and you should be fantastic. Okay, continuing on. Let's talk about rotations. Okay, a rotation isometry is usually done counterclockwise, so in this direction, and it's usually around the origin, but it doesn't have to be. Okay, some questions will tell you to rotate it around a point randomly in space. Okay, and if that's the case, if you want to rotate it around this point, say, then you can magically draw in or imagine as if this is your axis, and you can rotate everything from here. Okay, it's not hard to do using your imagination and your amazing brains. I know that you all have them, or you wouldn't be watching this video in the first place. So we're going to rotate this point ABC. Let's pick 90 degrees. We'll do a 90-degree rotation. So what I'm going to do, very tricky-like, is here we have the points -8, 4, -1, 6, and -3, 1 here. What I'm going to do is I'm going to literally rotate this whole entire grid around that orange center. Okay, so that we can talk about where it is that we end up. Now remember, this point over here is A, and B and C. So remember where they go. So watch A. Point A is now facing down. So let me draw that in here. So this is now A prime down here. This is now B prime, and this is your point C prime. Okay, here is C prime, here is B prime, here is A prime. Okay, let's go back and do that again. Let me show you where we were originally. Okay, here is your original points, A, B, and C. Now let's rotate it once again around that orange dot, and we end up down here at A prime, B prime, C prime. So let's look at these points now and see if we can find something in common with them, so we don't have to rotate this thing every single time. A is now at the point -4, 8, -8. B prime is at the point -6, -1. And C prime is at the point -1, -3. Okay, so let's take a look here. Here we had a point at -8, +4, and it went to -4, -8. Okay, -1, 6 became -6, -1. And if we're looking here and you notice some things, the -8s are the same number. The -1s are the same number. The -3s are the same number. They're just in a new position. So it looks like if we could write down a general rule for this that might apply to every single 90-degree counterclockwise rotation, I might say that whatever the x value currently is, it becomes the new y value. So it moves over into the y position as whatever it was. This -8 remains a -8. If this were to have been +16, this would be +16 and whatnot. So in general, it looks like your original x, your pre-image x, becomes your image's y value. And look at what happened to the 4. The 4 became a -4. The 6 became a -6. The 1 became a -1. It looks like our y value also changed places. but became negative. And I think this will hold true. You will see if you do a lot of these that this is a general rule that holds true for all 90-degree counterclockwise rotations. That to get the points, you simply have to switch your x and your y positions and make the y value, your new x value, negative. Okay? It turns out something similar happens with a 270-degree rotation, which is basically a negative 90. Your x's and your y's change places still, but now your new x, or your new y value, is the negative of what it used to be. Okay, it's the old value that changes. And a 180-degree rotation that you might guess, they both just become negative. Okay, let's show that over here with the picture. So -8, +4 under a 180-degree rotation. So if we move it over here, it's now at +8, -4. Okay, so just the x's and the y's just change signs. They don't change places when you do a 180-degree rotation. Okay, so hopefully that's helpful with rotations. If not, you can always just spin it around and see what you got anyway. Okay, and our last one is a dilation. A dilation can either be an enlargement or a reduction. Okay, if you have a scale factor that's larger than 1, you have yourself a enlargement. Things are getting bigger. A reduction, a scale factor between 0 and 1. Okay, less than 1, but a fraction, 1/2 or 1/3, or even 4/5 could be a decent one. It's a fraction between 0 and 1. Okay, so let's do an enlargement by a scale factor of 2 for this problem here, which means everything gets multiplied by 2. Everything is twice as far away. So if our a is at -3,1, under a scale factor of -2, it would be -6, +2. Okay, under a 2 times enlargement, or a 2 times scale factor dilation, b prime will end up at -16, +8, and c prime will end up at -2, +12. Okay, everything gets doubled when you're doing a dilation. Okay, and this is not an isometry because each one of these points will no longer be, the side lengths will not be the same as they originally were. So here's the -6, 2. Here's 16, 8, 9, 10, 11, 12, 13, 14, 15, 16, 4, 5, 6, 7, 8. Here's b prime way over here. And here's c prime, -2, 7, 8, 9, 10, 11, 12. Here's c prime here. So if we connect these with our nice and make a new triangle, here we have a prime, c prime. Here's b prime, c prime. And here is b prime, a prime. So notice, not an isometry. The pre-image, the image, is not the exact same size as the pre-image. Okay, it is twice as large. Actually, it's 4 times the area, but the lengths are twice as big. Okay, we'll talk about scale factor and what happens when you increase with areas later. Later on, there's probably another video somewhere out there, but we'll talk about that later on in the year. So here is your image, a prime, b prime, c prime. Now what's also kind of neat, artistically speaking, is we can draw a line from your center of dilation, in this case the origin, that goes through each of these corners or vertices, and they actually will match up exactly perfect. So there's c through c prime, here's a through a prime, and here is b through b prime. Okay? That way you can always check to make sure that your points are actually in line, because from your center of dilation through each of your vertices, they should all line up nicely to make a nice straight line. Okay, it looks like an actual little 3D image. It's kind of neato. But there you go. There are some geometric transformations. Rotations, reflections, and translations are all isometries or congruent transformations. And then we have a dilation, which is an enlargement or a reduction. Okay, fantastic. I hope you have a wonderful day. Thanks for watching.